Good morning, everyone. Let me first start off by thanking the organizers for all the hard work, of course, and for inviting me. It's great to see so many familiar faces and also to kind of meet new people. It's been great so far. So as Earl said, I'm going to talk about quantum complexity and error correction. And these are like several joint works with Anurag Anshu at Harvard, Chinmay Nirke at IBM Research, and Quinn Wang at Harvard. So the general theme of this talk will be an interplay between three different areas. First of all, complexity theory, quantum many-body physics, and error correction. And since everybody in this room lives and breathes error correction, let me start saying something about complexity theory. So as you may know, complexity theory deals with so-called complexity classes, which are collections of computational problems which are kind of related by some sort of resource cost. And in our cases, this resource will just be time. And like two very famous complexity classes are P and BQP, where P is the class of problems where the solution can be computed efficiently in polynomial time on a classical computer. And BQP is the class where we can use a quantum computer. Instead of computed, we can also ask what questions can be verified efficiently. And these are the classes NP and QMA. And here on the left-hand side, you see the known relations between these classes. So since everything that can be computed on a classical computer efficiently can be computed on a quantum computer efficiently, P lies within BQP, then NP is a superset of P, and then QMA is the generalization of that, so that kind of lies on top. Okay, and in this talk, I will mostly be dealing with the classes NP and QMA. So NP, just as a reminder, NP are all problems whose solutions can be verified efficiently. So, and this has two components. First of all, there's a proof, or also called a witness or a certificate, which is just some bit string. And on the other side, there's a verifier, which is some computing model. So, for example, a Turing machine or something of equivalent, which is kind of an equivalent computational model. And examples of these problems are, for example, factorization. So here the certificate will be just kind of giving you the prime numbers. You can just multiply them together and see that it gives you the right number. Or a proof of a mathematical theorem, where I just give you the proof. Or maybe a bit more exotic, satisfiability of Boolean formulas, where I just kind of give you the satisfying assignment. And there's an interesting notion called completeness. So there are so-called NP-complete problems, which are so general that they capture the structure of all problems in NP. So like a trivial example is witness existence, where I just ask whether an encoding of a Turing machine, given some input, accepts or rejects a problem. So it's kind of like just kind of capturing the definition. So it's kind of like maybe a bit boring problem, but there are other problems, so-called constraint satisfaction problems, which also capture this structure. So here the problem itself is just given some Boolean formula, just a set of clauses. Here this just means we have these variables and we can combine them, and then we kind of ask, can I kind of make it that the sum here will kind of turn out to be 0, so that all the clauses are satisfied, or is it true that for all assignments there's at least one clause which is not satisfied? Okay, so these are NP problems, and maybe you've heard of this, maybe you haven't, and then this was kind of just like a quick overview. However, the important part is that we can kind of extend notions of proof, And in particular, there's two ways of doing this. So first of all, we can make them quantum, or we can make them probabilistic. So how do we make proofs quantum? Very easy. Instead of talking about bit strings, we talk about quantum states. And the verification is done by some polytime quantum computing model. And in our case, this will be some family of circuits. There's some technical condition. They have to be uniform so that we are not allowed to encode some complicated solutions. Okay, and the class of all problems of this form is QMA. And this was introduced by Kitaev in the late 90s. And they are also equivalent complete problems. This is a so-called local Hamiltonian problem. And this is kind of a quantum version of this constraint satisfaction problem. And here, instead of talking about clauses, And the sum of all clauses, we just look at local Hamiltonian terms, and then at the global Hamiltonian. And now we are asking what is the ground state energy? And the problem is to decide, given some promise, whether the ground state energy is below some value or above some other value. Yeah? And it turns out that this problem is again kind of manages to kind of capture the full class of problems. Okay, so then the other notion are so-called probabilistic proofs, and this is something that's important in classical computer science. So these are the so-called PCPs, and this is something quite amazing. So instead of giving you the full proof, yeah, so instead of giving you the full answer to the solution, which you then check, it suffices to give you just a constant number of bits. Yeah. So in particular, in like more concrete terms, there's a so-called PCP theorem, which was proved by this set of authors, and then later much simplified by Iridino. And this states more precisely that every NP problem is equivalent to a problem where we only require access to a constant number of bits, and then we accept valid solutions with probability 1. Yeah, so we always accept correct solutions. But we would accidentally accept invalid proofs, yeah, with some bounded probability, yeah. And it's actually kind of something quite amazing if you think about it. So I could kind of give you a proof of, let's say, the Riemann hypothesis, and you check, I don't know, 5 bits of this proof, and then with high probability you would be satisfied that this proof is correct, without actually kind of going through the full argument. Okay, then. The reason why the PCP theorem is of such importance in theoretical computer science, besides being kind of like this kind of slightly crazy statement that you kind of maybe can't even believe if you kind of hear it for the first time, it also has other implications for approximations. Because it says for this NP-complete class of constraint satisfaction problems, that it's NP hard to decide whether whether all clauses can be satisfied, or whether actually some fraction, some large fraction is unsatisfied. Yeah, and this leads to a notion of approximate proofs. Yeah, so now any bit string, yeah, which fulfills most of, or like a large fraction of the clauses, gives us a probabilistic way of checking whether something is true or not. Okay, and with this we've seen how we can kind of take this complexity class NP, and we can generalize it in 2 ways. So we can kind of generalize it into a quantum way or into a probabilistic way. And now the question is, obviously, can we kind of combine this back into something that we call quantum PCP. Yeah, the statement would kind of look like this. So we would ask, can every QMA problem be converted in a way such that the verifier has only access to a constant number of qubits, and then decides on acceptance or rejection with some constant error probability. Yeah, and again, this kind of implies something for the quantum CSP version. So for local Hamiltonian, it says that it's QMA hard to decide whether there exists a state, let's say, with ground state energy 0, or whether all states are kind of gapped by some constant times the number of terms in the Hamiltonian. Yeah, and again, we can kind of now talk about these kind of approximate quantum proofs. So any state of energy which is kind of like below this gap is a valid proof. Okay. And yeah, this kind of led to this following notion. So what if quantum PCP was true? What it would imply is that approximate proofs should be very complex. Yeah. So and this we can measure by circuit complexity. So we can just look at the minimum depth of a circuit, which takes as input the all zero state, and produces the state of that we kind of want to measure the complexity of. And what quantum PCP would kind of imply is that these circuits can't be trivial. So in particular, it was conjectured by Friedman and Hastings that there exists some universal constant and a family of Hamiltonians such that the low energy states, so ones which have energy, let's say, below some fraction of the number of qubits, it must hold that their circuit complexity is large. So there can't be any way we can generate some approximation to the ground state which has low energy, and which can kind of generate very easily. Okay, let me kind of quickly go through why quantum PCP implies NLTS. And this is proved by contradiction. So assume that quantum PCP is true and NLTS is false. Then quantum PCP tells us it's QMA hard to decide whether the energy is 0 or bounded from below in a linear way. And not NLTS says we can always kind of find some trivial state which can approximate some arbitrary low energy state. So now we want to decide whether the energy is 0 or larger than some fraction. And by not NLTS, there exists this trivial state which approximates it. And if the energy is 0, like if this is truly we're in an exact instance, then we can classically check that we can just classically evaluate the energy. And this is true just by virtue of it being a trivial state. Otherwise, we are just in the reject instance. But this is exactly this kind of scheme that I showed you earlier. So this is exactly an NP problem where we just do classical stuff on a quantum state, and this would kind of mean that we can essentially kind of do QMA problems, like that QMA problems would lie in NP, and this can't be true. So this is the contradiction here. Okay, so this is the NLTS conjecture by Friedman and Hastings. That there are these families of local Hamiltonians. So assuming that quantum PCP is true, these Hamiltonians have to exist. And then otherwise, if this conjecture had been false, then this would have invalidated quantum PCP. Okay, and it turns out NLTS is true. So there are these Hamiltonians, and I will now kind of talk about how these Hamiltonians can be constructed and what this has to do with error correction. Okay, I kind of motivated NLTS a little bit through quantum PCP, and this is kind of usually how people talk about it, but I kind of feel it kind of stands on its own because it has some interesting implication for many-body physics. So in particular, we all know that on our scale, quantum mechanics is maybe not too relevant for our everyday life, so we don't see quantum mechanical effects. And this is because quantum mechanical effects are kind of entanglement and superposition, and they are washed out at non-zero temperatures. So just kind of decoherence kind of takes over at our scale, and we don't see any quantum mechanics. But we can ask a question: is this universally true? Like, can you kind of imagine a universe where quantum mechanics just kind of rules on all scales? And NLTS does say yes. Sorry, it just says no. So NLTS says there is a universe which you can kind of imagine where the Gibbs state is a non-trivial state. So in particular, you will have like large-scale entanglement everywhere. Okay, and it's kind of, I think it's kind of like nice that like complexity theory can kind of tell us something. Maybe, I don't know, maybe useful is a bit of a stretch, but kind of tell us something about nature. Okay, the NLTS conjecture kind of lies within like a whole zoo of entanglements. So this is a diagram kind of taken from this nice paper by Elder and Harrow from a few years back. And this kind of shows us like a few interrelated conjectures. So we've already discussed NLTS, which is this blob here. Then here's quantum PCP, which is this blob. And there's like a few other blobs. I won't kind of go through all of them. But the important part is that if one blob lies in another, it means implication. So quantum PCP we already proved that quantum PCP implies NLTS. And then there's something else called CNLTS and NLETS. Okay, NLETS was the first one that was proved. I won't kind of even give you the definition, but just kind of know that there's like these three works, which are very nice, which kind of prove this in using various constructions. However, all these constructions, if you think about it as like a physical model, they were all low-dimensional and Euclidean. So they lived in Euclidean space. And we already knew that NLTS Hamiltonians cannot live in Euclidean space. So if you want to have some physical system where the ground, like the approximate ground states are very highly entangled, it can't be on a Euclidean lattice. And the argument is quite nice. So assume that we are on some Euclidean lattice, like L by L by L, whatever dimension. Then we can just subdivide it into these like small L by L, whatever, subregions, yeah? What we then do is we can, since we assume that this is a constant block, yeah, we can take a quantum circuit and just generate the state in constant depth on here, yeah? So we just kind of make sure that, like in the bulk, we actually do satisfy all the Hamiltonian constraints. And then we don't care what happens at the boundary, and there we pay some energy penalty, yeah? But this energy penalty essentially kind of goes as 1 over L times n, where n is the number of particles that we have, yeah? But since we can kind of we can choose L arbitrarily, it has to be constant, but arbitrary, we can always kind of beat this universal constant that the NLTS theorem kind of asks us, yeah? So yeah, we can always kind of undercut the energy cost, yeah, due to this like bulk boundary scaling, yeah? So Euclidean space is completely ruled out for this type of universe. Okay. Yeah, before I kind of talk about NLTS, let me kind of give you a weaker form of NLTS, which is called CNLTS, for combinatorial NLTS. And instead of low energy states, so where we kind of just ask that the energy of the state is below some constant times the number of terms in the Hamiltonian, or the system size, let's say, we ask for states which violate only a few terms. Yeah? So this is just kind of counting the number of terms where I do pick up energy in my Hamiltonian. And this is strictly weaker because you can imagine that there are low energy states which violate all terms, but by very, very little. Yeah? There's like some kind of like very low frequency mode kind of going through, and it just kind of violates everything like a little bit. And here we're just kind of counting. Yeah? This is why it's called combinatorial. Okay. Yeah, this was kind of like the next one to fall. That was that CNLTS Hamiltonians exist. That is work by Anurag and myself. So let me kind of talk a little bit about this, and then kind of we kind of move over to NLTS. The idea here is the following. So we construct our Hamiltonian using some tensor network, and this tensor network implements a classical code. So now I'm kind of start talking about error correction finally. And the nice thing is this construction has actually the right geometry. Yeah, so the idea, what we kind of use are so-called expander graphs, which are kind of ubiquitous in theoretical computer science and also like classical coding theory and also more and more in quantum coding theory. And these are well-connected and sparse families of graphs. Well-connected here, really, sparse just means yeah, they just have like a small number of, like every vertex has like only a small neighborhood. But well-connected means that if I look at some subset of vertices, let's say, then the number of edges which connect the subset with its complement must be large. Yeah, and this is kind of captured. Oops, this is kind of captured by this constant here. Okay. A kind of classical result in classical coding theory is due to Zipser and Spielmann, who showed that we can use these expander graphs to define good LDPC codes, yeah, classical LDPC codes. Where LDPC, I mean, maybe I don't need to define it, but LDPC just means that we have very sparse checks. And the idea here is we take these expander graphs and we equip them with local checks around each vertex. Yeah? So the edges are bits, yeah, just in the toric code. Yeah, actually, just imagine the toric code, like one half of the toric code. But instead of doing like a total parity check at each vertex, we do the parity checks of some other code. Yeah. So for example, here we have a neighborhood with seven bits. So imagine we just have to do the parity checks of the 743 Hamming code. Yeah. And this would define some kind of global code if we do this on every vertex. Yeah. I just want to mention it was kind of like a nice work by Mishulam, kind of showed that this is actually the same thing as something which is kind of known in mathematics as homology with local coefficients. And I will kind of borrow this notation. But kind of this just means like this is just a code defined by the graph X and this kind of local system or local code the way that I associate with every vertex. Okay, and this is kind of what the code words would look like. So let's say the local code has distance 3. Yeah. Then if I kind of draw my edges where I have a 1 in red, yeah, then I would kind of see that around every vertex here, I would get at least 3 red edges, yeah, because of the local code having distance 3, yeah. And then, I don't know, once you kind of build up your code word of the global code, you see that, yeah, you kind of get this kind of spider web. And yeah, the nice thing that Zipser and Spielmann proved was that if your graph is expanding enough and your local code is good enough, then the distance of the global code, yeah, so the number of red edges you see here, is a constant fraction of n. Yeah, so you have a linear distance code. And we kind of took this idea and implemented these codes within a so-called perturbed tensor network. And this kind of gives rise to this local Hamiltonian that we used for the CNLTS construction. Yeah, so we just kind of take our code, our graph, and turn it into the tensor network is actually called more specifically projective entangled pair state, or PEPS, where we replace every edge or bit by an EPR pair and enforce the local checks simply by projectors. Yeah? So I just kind of project onto the local code words. Okay, yeah, and then the state I get out, like our PEP state, is the uniform superposition over all these code words of the Spielmann expander code. There's a technicality here where we actually require this to be a unique ground state, yeah. And so we can't just kind of use PEPs and projectors because there might be other states that would kind of pop up. However, we can kind of enforce this by making the projectors full rank, yeah. So we just kind of perturb it by some little delta, and then kind of this gives us our Hamiltonian. And usually I would kind of just brush over this and kind of just sweep this under the rug. But there's some payoff later on, so keep this in mind. Okay, all right. So we have seen that we can kind of get a family of Hamiltonians such that the low or like the number of the states violating only a few terms are kind of given by code words where we violate a few checks in some Spielmann expander code. Yeah. And I will call these epsilon approximate code words if it's just some epsilon fraction of the total number of checks. Okay, and now this is kind of like the main observation which kind of underlies the whole thing. And I will kind of keep repeating this through the rest of the talk, so don't worry if you don't get it the first time. The observation is that these approximate code words, they cluster, yeah? Which means they're either very, very close or they're very far apart in Hamming distance. Yeah? So this is what it kind of looks like. So if this is my Hamming space, so all bit strings, yeah, then there's maybe some code words, which are these black dots. And then the green bubbles are my approximate, or like the bit strings which violate only a few checks. Yeah, so this would what this would kind of look like. So here's like one code word here, and then there's here another code word, yeah. And I would need like order n bit flips to kind of go from one to the other because it's a linear distance code. Okay, so now you kind of might see, okay, maybe he messed up. He didn't draw code words in every bubble. But actually, there are situations where we don't have this. So here's like a kind of like a fun example. So imagine this dumbbell repetition code, or you can also think of it as an Ising model on this dumbbell, where I just do parity checks across nearest neighbors. Then these would be some approximate code words where, let's say, everything is in the one, like everything is set to 1, and then maybe like a few things are kind of flipped, and then I would kind of pick up some energy here. But see that I can kind of flip everything on one handle of the dumbbell, and everything is not flipped on the other side of the dumbbell. And I would only pay like a small energy price here. Yeah, and this would be like something which is not close to any code word, yeah, but still kind of far apart from everything else. So there might be like kind of bubbles which are kind of separated, but kind of yeah, not surrounding a code word. Okay, so at this stage you might have some open problems because I kind of set things up, and now I'm kind of talking about clustering. So first of all, how can we show that approximate code words cluster? And then what is this to do with anything that I talked about earlier with like complexity theory and circuit lower bounds. But I will kind of not talk about this now, so I will talk about NLTS first. So NLTS, because then the whole reasoning is, essentially I can kind of interleave the proofs of CNLTS and NLTS and save some time. Okay, so NLTS, the proof is based on the same observation, but using a very different construction. So here the Hamiltonian is not some PEPS tensor network, but it's the code Hamiltonian of a good quantum LDPC code, yeah? Where good means it has sparse checks. LDPC means it has sparse checks, and then good means the number of encoded qubits is linear in n, and the distance is linear in n. And we can construct these codes using something called a balanced product, which is kind of like a classical construction from like algebra and topology. So in like previous work with Jens Eberhard and I, we defined balanced products to de-randomize some earlier nice work by Haar and Hastings and O'Donnell. And we also kind of gave a way to take two of these Zipser-Spearman expander codes and combine them in a way that we kind of conjecture would give good quantum LDPC codes. And this conjecture was proved very nicely by Panteleev Kalachev, who gave this very nice distance bound, which is like a very hard technical work. And they kind of did this for a Zipser-Spearman code and its balanced product with its dual. And similarly, this can be done, as was shown by Dino and others, by just taking like two Zipser-Spearman codes directly, so we don't dualize one of them. And then we kind of get another good QLPC code. And what I kind of draw here is, okay, so we can have take these graphs, X, and kind of equip them with these local codes. But there's some kind of notion from homological algebra that I kind of won't go into, that this is kind of equivalent to taking the balanced product of the two graphs in itself, which kind of gives us some high dimensional object. And then we equip this with something called a tensor code. And then the third construction that popped up in the literature was by Levrier and Seymour, where they take this high dimensional object and essentially do something like the rotated tori code version of this. Yeah. So with the tori code, what we can do is we can kind of think of the tori code as taking a product between two repetition codes. Yeah. And then we obtain Kitaev's tori code, but then we can kind of make it more symmetric by doing some procedure where we put qubits on the vertices now and have our checks to be faces. Yeah? And this makes it a bit more symmetric. And exactly the same kind of reasoning kind of goes through with these balance products. And this is kind of what Levrier and Seymour did. We can play other games. We can take Kelly graphs of other finite simple groups. We can take lifts and so on. But I would say it's kind of always the same recipe. Okay, so these are our second set of Hamiltonians, which I will claim are NLTS. Okay, now we're kind of now back to clustering and how we can kind of show that the code words cluster. Okay, and here's the idea. So it turns out that we can kind of show clustering through expansion. So let's say, kind of forget about what we said earlier. So now we just kind of talk about some very general definition. So just take some binary matrix A. It can be a parity check matrix, but it doesn't have to be. Then let's call this alpha beta expanding if on some subset V, which is important, if for all bit strings which have small Hamming weight, yeah, in terms of like the total number of bits, then if this is a parity check matrix, then the syndrome will be lower bounded by the weight of this bit string. Yeah? So if this is an error, then the syndrome will be lower bounded, like the size of the syndrome will be lower bounded by the size of the error. Okay, and then clustering, let's kind of make this more precise. So it's called epsilon mu nu clustering on some subset V. If for everything which has low syndrome, yeah, things are either close by or far apart. Yeah, these are this mu and this nu. Yeah. Okay, and now it turns out that there's a very simple lemma which shows that if the parity check matrix is mu epsilon over nu expanding, on some subset, then it's also epsilon mu nu clustering on the subset. Yeah? Again, I kind of want to highlight that we can kind of choose arbitrary subsets here. Okay, so yeah, and here we kind of see what we kind of are after. So here are our epsilon approximate code words for CNLTS, and here is our clustering property that we are after. Okay, so first of all, for CNLTS, it's very easy to show that the parity check matrix of the Zipf-Spearman expander codes are expanding. Yeah, and this lemma then kind of tells us what we want to know. And similarly for NLTS, where we now kind of deal with these higher dimensional objects, we can show that if we choose our subsets right, yeah, if we look at the let's say the smallest representatives of approximate X logicals, yeah, and we look at our X parity check matrix of our CSS code, then we can apply our lemma, and we see that approximate X and Z logicals cluster. Okay. Yeah, and this is kind of nice because this is kind of like what I kind of showed earlier. In some sense, is like a generalization of some other expression called minimal boundary expansion, which kind of people in TCS know very well, like in the community of high-dimensional expanders, for example. Okay, so now we know that either code words or logical operators cluster. But yeah, what does this have to do with circular lower bounds? So we are almost there, actually. So if we look at some probability distribution, which is determined by some state psi. Yeah. So let's say we have some state psi, and let's say it's kind of some state which is generated from the all-zero state by some unitary circuit U. Then we can kind of measure, let's say, psi in the Z basis, yeah, and this kind of gives us some probability distribution on psi, yeah. So let's just take some subsets of bit strings and assume that these have high mass on our probability distribution. Then it turns out that the depth of U has to fulfill this relation, yeah. So in particular, if we have high mass here and there, and these are kind of far apart, yeah, the distance here is of order n, yeah, then we get a logarithmic lower bound on our circuit that generates psi. Okay, and now the rest of the argument is essentially just kind of carrying everything through. So we have our low energy states which are concentrated on clusters. Yeah, that means that our probability distribution is concentrated on clusters, and therefore the low energy states must have high circuit complexity. And that's the argument for NLTS and CNLTS as well. Okay, but now the question is, how do we move beyond NLTS? So the quantum PCP conjecture is still wide open. And just to remind you, quantum PCP tells us that it's QMA hard to decide whether the ground state energy of some local Hamiltonian is less than a given number or larger than this number plus some constant here. Yeah. We can have make this like a little bit weaker, so we can have ask about polylog weak versions, where instead of a constant here, we have something which vanishes as 1 over a polylog, and this is also still unproven. However, what I want to kind of point out is that that quantum PCP is a statement about computation, yeah, something which is dynamic, whereas what we talked about it is just constructions which are static, yeah, which are about states and code states and so on. So how can we kind of get computation into the game? Okay, and turns out that a very promising approach is kind of going back to CNLTS, and this is kind of why I was kind of dragging CNLTS around for the whole time, even though it's kind of superseded by NLTS. So we can use some tensor network to encode a quantum computation into a Hamiltonian ground state. And this is this new work by Anurag Anshu and Quinn Wang and myself. Yeah, so let's say we have some circuit, quantum circuit. Then we can turn this into PEPs. Yeah, this is well known that yeah, the relationship between that we can kind of do this, and this is kind of very similar to MBQC. So we just kind of create some resource state with EPS, and then the computation itself is just kind of affected by measuring in our projectors. Okay. However, remember, I kind of asked you to kind of remind some fact, which was that we can't just use arbitrary projectors. In this case, it turns out that this would just kind of give us a model which is far too powerful. However, we require these perturbations. Yeah, that was kind of important for us to kind of pin down a unique ground state with our Hamiltonian. Okay, but this perturbation turns out I can rewrite, right? Like everybody here well knows that I can write the identity as some superposition of Pauli's. Yeah, and if I then kind of define my model, it turns out that this turns out to be, if I just kind of do it naively, then the computation I get out is just one which is affected by IID depolarizing noise. Yeah. So now I have a circuit to Hamiltonian mapping, but the computation, the virtual computation which is encoded in the Hamiltonian, is noisy. Yeah. But we know how to deal with this, right? We can just use quantum fault tolerance. So this was kind of great. So we can just use off-the-shelf fault tolerance constructions and kind of deal with the noise inside the model. Okay, and yeah, and it turns out this I think we believe is a step towards this poly-log weakened quantum PCP conjecture. There are some other things. So first of all, it turns out that we kind of believe, and we have like good evidence that violations which are due to the quantum PCP, yeah, which are can be kind of arbitrary, can be kind of mapped onto adversarial errors. Yeah, so there's like some statistic noise due to the model, and then on top of this, there's adversarial noise that we have to deal with. Yeah, and we can kind of expect like 1 over depth of the circuit of such errors in our computation. Yeah, so we kind of have like a bound on how many of these kind of show up. Now, the good thing is, like, this is not too many, because we can do QMA verification in polylogarithmic depth. Yeah, so there will be like polylogarithmic many adversarial errors showing up in our computation. Yeah, and what we kind of also show in our work is that, yeah, if you look at these combinatorial states, then these are actually states kind of undergoing adversarial noise. So now what's kind of missing is, so if we kind of show that this statement kind of holds for arbitrary 1 over poly D energy states, and we had some fault tolerance theorem which can deal with adversarial noise, then the polylog weak quantum PCP theorem follows. Yeah. So this is kind of like an implication we show. Yeah, and that's all I had to say. So let me conclude. First of all, we have shown that good quantum LPC codes give rise to NLTS Hamiltonians. NLTS is kind of interesting to quantum PCP, but also has like kind of stands on its own by kind of showing that thermally stable entanglement is possible in some kind of strange universe that we can build. And finally, the CNLTS construction plus some strong quantum fault tolerance theorem kind of points towards a polylog weak quantum PCP theorem. And yeah, with this, I thank for your attention.
Thanks for a great talk, Nico. Do we have any questions? I've got one over here.
Yeah, thank you for a very nice talk, first of all. I had a question about your second point here, which is that if you just want non-trivial states as like Gibbs states at a finite temperature, you can get that in finite dimensions.
Okay, so I'm at a math institute. So I mean, I know it's so people kind of you would point out to the 4D Tori code, for example. Right. I think so my point was more like this is kind of like first rigorous proof of this. But yeah, I mean. Yeah, I think I know. If I talk to physicists, then they usually say like, "Oh yeah, we already know this," but now there's like a mathematical proof of this.
But do you also think that there are implications that kind of go beyond that are only possible in these non-Euclidean geometries?
So you're asking whether I would conjecture that like only in non-Euclidean geometries it's actually true, or?
No, more like, is there some conclusion for many-body physics that goes beyond just thermal stability as a Gibbs state?
I'm not too sure. I mean, like, there's definitely kind of things which can happen in like curved spaces or like like non-Euclidean spaces, which are kind of interesting from like a many-body perspective. And maybe we can talk about this later. So there's like some other interesting stuff that can happen. Yeah, I'm not sure whether it's too interesting necessarily for many-body people, like because it's kind of hard. I would be hard pressed to kind of find like systems where you can have engineer like curvature. I think there's like some work where we kind of have defects, and then this kind of on like large scales kind of looks like hyperbolic space in a Euclidean lattice. But yeah, but I'm also not like a super expert on this. So.
And maybe just one small follow-up question is, does this also imply that the code itself, the LDPC code, is thermally stable and that you can encode the same amount of information at finite temperature?
Yeah. So I mean, if you kind of build like if you could engineer this Hamiltonian, then yes. But I mean, like usually we can't do this, right? Like usually we still have to kind of rely on like active error correction. Like even with like if you would build the 4D Tori code in a like system, then you would still kind of do active error correction there. Thanks.
We have one question. We have one question from Slido. So, what is the role of good code when you use quantum LDPC codes in achieving clustering of code words? Would locally testable or locally decodable code suffice?
Oh yeah. So yeah. Maybe I should have said this. So in this earlier work by Elder and Harrow, they showed that QLTC code, like the existence of QLTC, would imply NLTS. And the funny thing is, we kind of circumvented this. So if I maybe go back, maybe not so far. Where's my clustering? I have so many pictures of clustering, and now I can find them. Ah, here we go. There we go. No. Okay. Okay, let's take this one. So I made a point of like not there being like a code word in every cluster. If there was a code word in every cluster, this would be QLTC. Yeah. But we kind of completely avoided this. So we can have these clusters which don't have code words in them. So this is not necessarily a QLTC code, but still the proof kind of goes through. So we kind of completely sidestepped this issue of kind of constructing QLTCs.
Hi. So on your example of the like dumbbell thing, where you like don't have, I guess it's connected to the last question, where you don't have the code words in every blob.
Yeah.
To actually construct this example, you have to have like a non-expanding graph, right? Because it has this big bottleneck in the middle.
Yeah.
So in the case where your graphs obviously are very strongly expanding, do you have some intuition for how these like non-code word blobs arise?
You mean what they look like?
Yeah, well, just because like my intuition is that you need something like this, where like the only case you can imagine is like this, where the graph is not an expander. So I'm curious how it happens when the graph is an expander.
I mean, it's a very valid question. So the thing is, just I don't think I have any like geometric intuition for this, and it's not disproven, right? So yeah, there's nothing we can say at the moment.
Okay.
Yeah, but it's a very good question. But yeah.
Okay, thanks.
Thank you for the great talk. You were mentioning your conjecture about good construction on good LBC codes. So I think this kind of conjecture is in your paper. I know, but if I open the full proof of Pantelev-Karachev and the later constructions, there are a lot of details to be shown, and if you look all these proofs from a viewpoint, what was your? I mean, if you give conjecture, I think you knew at least partially something that like at least something that convince you to give this conjecture.
Oh, yeah, of course.
Yes.
Yeah.
So yes, it'd be very good to clarify which part is in your paper, and then what was their crucial contribution on the top of your partial results. What makes the full proof possible?
Well, I mean, the construction is in our paper.
Yes. Okay.
Yeah. Like the construction is on our paper. And
there are several constructions, right? Three different.
So I mean, there's like the construction where you take valence products between expander code and a cyclic code. Yeah. So this is kind of like the abelian version, which we kind of which also like Hastings, Howe, and Donnell, and also Papadantalev Kalachev had before. And this kind of I know necessitates some kind of abelian product. Yeah. But then what we kind of contributed is essentially, this like non-abelian balance product, yeah? And this is kind of like the thing where you take two expander codes and kind of combine them. And this is exactly what all of these constructions are.
And what was the remaining unknown when you give this conjecture? And then
so you can maybe check my QRP talk, so I kind of talk about this explicitly. So the thing is, in the previous construction, you had this thing where you like one logical was essentially a code word of the expander code. Yeah, so one side was exactly linear distance, and the other side was just like this kind of cycle, which was like, I don't know, like square root of like third root or something like this. So the way you can have kind of avoid this is by taking just two expander on both sides, yeah, and then both sets of logicals will be of linear distance. So that was like the strong intuition, and you can also there's many ways you can kind of think about this, but this is I think like the most geometric way of thinking about this, yeah. So you can kind of check out my QRP talk, and there I kind of explain this.
And then if you look the Panteleimon, okay, maybe yeah, I'll talk later. But thank you very much for clarification.
Okay. Let's thank Nico again.